Welcome to a lecture video on using MCMC methods for classification. We're going to be using logistic regression and do some Bayesian parameter inference using PyMC3. So let's start with a quick review of Bayesian logistic regression, or just of logistic regression. So logistic regression here is a standard plot. Remind us what we're doing. We have some set of inputs, one or more variables that we're going to use as our regressor variables. And so in this case, we have a balance, and we're going to predict whether somebody's going to default or not. So we plot the non-defaults as 0 and default as 1. And our logistic regression allows us to estimate this probability curve, which is the probability of defaulting based on the balance. Now we can, of course, have one or more regressor or input variables, and we want to predict this probability curve, and we predict it by finding the curve that gives us the lowest error, and the error would be the distance between these vertical value here down to the curve, squared and summed. And so we find that curve using this formula. This is the formula for that probabilistic curve. This is the logistic function, and of course this logistic function only has a intercept and a single variable, but you would have plus your additional variables as you go out. Now, of course, you can use logistic regression for a binary output, 0, 1, default or non-default. You can also use it for multiple outputs. Here's an example showing some figures that may be familiar, showing prediction of 3 classes on iris data. And here's our 3 classes depicted as green, blue, and red. Iris data is 4-dimensional. There's 4 input variables. And so this is showing correct classification with circles, incorrect classification as x's, and we only have 2 dimensions to plot in, so the x's don't exactly line up with where points sit in these 2 of the 4 dimensions. And so our separation surfaces are always going to be linear in this logistic regression classification. And just for sake of comparison on the iris data, logistic regression, here we have training data, cross-validation, and test data, has a slightly higher error rate than QDA or LDA. This is just on the iris data. This is not in general. Logistic regression is sometimes more accurate. It depends on how well we can model our data with a Gaussian distribution, right? Of course, LDA and QDA assume you have a Gaussian distribution. LDA has, logistic regression has more relaxed assumptions. And so logistic regression can sometimes be more robust against overtraining than LDA and QDA because it has more relaxed assumptions. But if your data satisfies that Gaussian distribution, LDA and QDA would be more likely to give you better results. So that's a quick review of logistic regression for classification. And so let's go through using PyMC3. And of course, we're doing MCMC methods. So our goal in this is to do some sort of Bayesian inference on the parameters, right? And so let's walk through this notebook that I've set up to allow us to do this Bayesian inference using the PyMC3 library. Or the PyMC3 package. So the first thing we're going to do is import our packages. We're going to use PyMC3, Pandas, and NumPy. And for plots, we're going to use Seaborn and Matplotlib. And so we can execute these by hitting the Run button. I have already executed them. This next block of code is just defining a function that's going to help us with some of our plotting. We don't need to get into the details. You're free to look at it on your own, of course, but we don't need the details for that. Now we're going to take a look at our data. We're going to read in our data with this pd.read CSV, that's from Pandas, and we're going to look at the header of the data, and then this is the head of the data. So this is just the first 4 observations, the 4 features for each observation, and then the class. Now we're going to use a Seaborn library for plotting, and so I've executed these commands, so I just need to click on this right-hand side. That'll show the results. I've done that to speed up our analysis here so we don't have to watch them execute. This is the pair plot in Seaborn. And then we have some extra information here to color the output in the pairs plot by the species, or in this by whatever class we're going to assign them to. And we're also going to designate markers for the different classes. And then of course the pairs plot gives us these nice histograms along the diagonal if you do the pair plot in Seaborn. Now I want to avoid talking too much about what we would infer about these parameters. There's a little bit you could infer from that pair plot, but that's going to be part of your homework assignment. So if you're seeing things that you think are interesting, remember those for when you do your homework assignment. Now, this is the step where we're going to do our MCMC work. And so we're going to, you'll notice here we don't assign any priors, and we're allowing PyMC to assign its default prior. And so we have that here, that the prior probability of theta is going to be a normal distribution with 10 to the 12th times I, and so that's an extremely weak prior. And so we can execute that, which uses the NUTS sampling. NUTS is a Hamiltonian sampling method. It does a good job generally. And so that would be the output. And now we can look at the variables. Trace is the primary output. Let's scroll up a little bit and see. Trace equals PM. PM stands for PyMC3.sample, and we're going to do 1,000 samples to build our trace plots. And then trace here is a structure. It has a lot of information in it. And so one of the things, you can just grab the variable names off the trace, and we just include that for convenience. And now we're going to take a look at the output from MCMC methods. And so we're going to use this plot traces, which does a trace plot, which we've seen before, but does a little bit of extra plotting on top of our trace plot. And so that gives us this trace plot here, which should be fairly familiar with. This right-hand set of plots shows you the MCMC sampling using the NUT sampling. And on the left-hand side, we have a plot of the probability distribution for the intercept, sepal length, sepal width, and we've added to these trace plots the mean, and shows where the mean is. Then we have what we call a forest plot, what's called a forest plot, and let's show the forest plot. The forest plot shows the 94% credible intervals, and so for each of our regressor variables, we have a circle which shows us the median value. We have the IQR, which is the 25% to 75%, or the middle 50% quartile range in the dark lines, and then the outer lighter lines show the 94% credible interval for each of the different variables. And then the third plot we're going to show here shows the posterior probabilities for the different regressive variables, but it shows them plotted together. So this plot is what's called a joint plot in the Seaborn plotting library, and it's plotting the trace posterior probability for sepal length together with the posterior probability for sepal width in trace. And so this is petal and petal, and sepal and sepal. And for your homework assignment, you're going to be inferring some of the information about those different regressor variables. Just to take a peek at what else you can do using logistic regression and the parameter inference. So this is an example that's part of the PyMC 3 library. And the goal here is to use logistic regression to predict how likely am I to make more than $50,000, depending on some of my demographic factors. And there's also, in addition to what we're going to look at, there's some exploration of model selection, which is something you're going to look at in future chapters. So there's a lot to the code here, which we're not going to get into. Here's all the different variables, input variables. There's some parameter cleaning, some plots. This is a notebook that you can look at your leisure. And I just want to take a look at two things that are done in this notebook that are in addition to what we've used on our iris data. So there's this PyMC plot posterior predictive GLM. And what this allows us to do is to look at a couple of different models and plot the posterior predictive probability and get a measure of the uncertainty based on variation in some of the input parameters. And so let's scroll up here. This block of code builds three separate linear models, LM, LM2, and LM3. And each of those linear models looks at the data and it inputs this value here, 12 or 16 or 19, and this has to do with the number of years of education. And then that calls this function that's defined here, and so it builds a linear model with picking just restricted to certain levels of education. And then this block of code does the plot. It creates this plot here, and I have it in a larger plot that we can look at. So the vertical axis is the logistic regression output probability, and it's the probability of having any income greater than 50,000. And it's that probability plotted as a function of age, and so that much would just be logistic regression. What the PyMC3 gives us is this measure of uncertainty as it varies over the ages. And so you can see that the high school education has a probability of getting greater than 50,000 that follows the blue curves, and each of these different blue curves comes from a different Monte Carlo run. So that gives you a measure of the spread of uncertainty within each of these different classes. And as another additional, these are just things that are interesting, that are nice to know, that there's a lot more in PyMC3 that you could explore. You could also plot the results for the odds ratio, something that's particular to logistic regression, that you can compute these odds ratios. So it's the ratio of getting over $50,000 versus not getting over $50,000 based on some of your inputs. And so this gives you a measure of the uncertainty for the odds ratio. Normally we do logistic regression and we get one value for odds ratio, and of course with MCMC methods we get a measure of uncertainty through our Bayesian methods. And so this gives us a measure of the uncertainty about the odds ratio, not just that the odds ratio is declared to be about 1.395 in this case, but what the spread is in our certainty about the odds ratio. Well, I hope you enjoyed our tour of using logistic regression with PyMC3 using Bayesian Monte Carlo MCMC methods. Thank you.